A problem that I didn't assign on the homework but might be useful for you is AP 7.3 out of the Dorff-Bishop text. So this problem gives you a transfer function, open loop transfer function, GC of G, that's 10 over S times S plus 1 times S plus P. And it asks you, can you sketch the root locus as a function of P? So first of all, this does not look like root locus. Root locus looks like 1 plus k times some open loop transfer function equals 0. Or you can remember that it's k times the open loop transfer function equals minus 1, or 1 angle 180. So because p is not a multiplier in front of this transfer function, we can't use what we know about root locus in order to sketch this root locus. So you could put it into MATLAB and vary p from 0 to infinity and see where the poles turn out to be. But I'd rather actually sketch it as a root locus. So let's try to make this function look like 1 plus p times some open loop transfer function equal to 0. So how can we do this? Well, let's close the loop and find out the characteristic equation. So y over r becomes 10 over s times s plus 1 times s plus p plus 10. And if we multiply this out further, we can multiply in the p's through these multipliers of the parenthetical transfer functions. This doesn't really seem to help here. This does. So now we have p isolated all on its own. 10 over s cubed plus s squared plus 10 plus p times s squared plus s. So now we can take this transfer function and label it as 10 over some delta of s. And now we're going to try to map delta of s to something that looks like our root locus equation. So if we divide through everything by s cubed plus s squared plus 10, we end up with our characteristic equation delta of s 0 equals 1 plus p times s plus 1 over s cubed plus s squared plus 10. Or, just like we saw with root locus before, now we have p times some open loop transfer function equals minus 1. It's not the same open loop transfer function we saw before, but it's some transfer function that we can use, and this is going to tell us how the root locus will vary as we vary the value of p. So here we have zeros at 0 and minus 1, and we have poles at 0.77 plus or minus j 1.826 and minus 2.54. So based on this, we now have some GOL hat, which looks like s times s plus 1 over s plus p1, s plus p2, s plus p3. So with this in your mind, now you can go ahead and sketch the root locus according to p. I'll go ahead and do it, but you might want to pause the video now, do it on your own, and then check to see how well you did according to the comparison. Of course, you can always do this with MATLAB as well, but MATLAB doesn't show you the intermediate steps. Okay, so let's go ahead and sketch the real and imaginary axes. Remember that our zeros are at 0 and minus 1, and we have poles at 0.77 plus j 1.826 and at minus 2.54. So go ahead and lay those out. I've sort of labeled our points here. So we have our PZ map. We label the points that are on the real axis here. And now we need to find the location of the asymptotes and the angles of the asymptotes. So we have one more pole than 0. So we end up with k equals to 0 as our only choice, and so our only asymptote is at 180. We could go ahead and calculate sigma a, but it doesn't really make much sense to do so since this asymptote only heads off at minus 180 degrees. So where's our breakaway point? Well, to calculate the breakaway point, we create this imaginary function minus 1 over GOL of s, and we take its derivative with respect to s. So we can go ahead and do that. We get some quotient a over b. You guys know how to do this because you've all had calculus. Solve for 0. And our pole values, our values that optimize this equation, which is the potential breakaway points, are at minus 0.5, 2.275, and minus 1.9 plus or minus j 2.3. So which of these points, 0.5, this is on the real axis, and none of the other points are. So that's our breakaway point. And now we know that this breakaway point is going to head off to the middle of nowhere. So where does our j omega cross? So we can calculate using Routh-Hurwitz and this value of p. Now we can calculate the value of p such that we'll get a 0 in the left-hand column of our Routh-Hurwitz analysis. So our Routh array is going to look like 1 in p, and then p plus 1 and 10. So now using the Routh analysis, we'll calculate b1, and then c1 is just going to be 10. So clearly the value for b1 is going to be the interesting value, because s2 will only be 0 for p equals minus 1, and we don't allow p equals minus 1 in the root locus. So we solve to make b1 equal to 0. P times p plus 1 minus 10 equals 0, or p squared plus p minus 10 equals 0. This gives us values of p of 2.7 and minus 3.7. So at minus 2.7 and minus 3.7 are our potential values of p that are going to give us a 0 in the left-hand column. So clearly minus 3.7 doesn't make sense, so for again p equals 2.7, this is going to give us a root that's on the j omega axis. So we plug that in, 2.7 plus 1 s squared plus 2.7s plus 10, and we solve for s. So these values are at 0 plus or minus j 1.64. So we'll go ahead and label those on the axis here. Primo. So we know, by the way, that the root locus always starts at poles and ends at zeros. So we know that we're going to start at these poles here and head towards the 0. We'll intersect the real axis and then turn over. We know where we're going to go through the j omega axis, right here. The only thing we don't know is the angle at which we're going to be leaving these initial poles. So let's go ahead and calculate, in this case, the angles of departure. So to calculate the angle of departure, you'll remember that we go ahead and define these points and the angles between each of our individual poles and the zeros that we're trying to find the angles of arrival to. So in this case, we're actually labeling everything except this first pole right here, and we're leaving that angle as an unknown, angle 5. So let's go ahead and calculate the angles between each of the known poles and zeros, and this pole at some epsilon far away from that pole. So the angle 1, angle 2, those are two of our 0 angles, and then 3, 4, and 5 are our pole angles. And we know that has to equal plus or minus 180 degrees. So angle 1 is the tan inverse of 1.826 over 0.77, which gives us about 67.1 degrees. And by the way, we know where that is because our pole value is at 0.77, and the height is 1.826. So we're calculating these from the values that we already know from the poles. Angle 2 turns out to be 45.9 degrees. Angle 3 is 90 degrees. And angle 4 is 29 degrees. So by adding all these up and solving for 5, we determine 173.67 degrees. So now we know the angle at which we leave, which is just above 180, and then it cruises down and crosses the j omega axis.